Welcome to the deep dive, where our mission is simple: extracting that crucial knowledge from complex topics, saving you tons of research time. For you, the learner, we get it. You need to grasp technical stuff quickly, effectively, without getting swamped in detail.
Exactly. And today, we're tackling something really foundational: core system design concepts. Think of it like getting a solid handle on how modern web applications actually work and, how they scale up.
And before we jump in, just want to mention this deep dive is brought to you by Stonefly.com. They're a solution company in data management with, wow, over 2 decades of experience. Pioneers in SAN, NAS, S3 object storage, backup and DR, cloud, AI advanced security too.
Yeah, and what's really interesting is their integrated approach.
Yeah.
Things like snapshot, encryption, replication, deduplication, it's all built in. Plus, their focus on AI integration and building like cyber-resilient architectures is pretty forward-thinking. Their object lockdown technology, for instance, is a big deal for ransomware defense.
Good point. And Stonefly.com, the solution company in data management, they've served all kinds of big enterprise customers: finance, healthcare, legal, education, government, you name it. So yeah, when we talk robust systems, companies like Stonefly.com know what they're doing. Okay, let's unpack this. System design. It's the guts of the internet, basically. Where do we start?
Let's kick off with the absolute core: client-server architecture. I mean, this is the fundamental interaction you have every time you go online. You've got your client, your browser, maybe a mobile app, and then the server, which is just a powerful computer that's always on, waiting for requests.
It's like ordering at a restaurant, isn't it?
Yeah.
You're the client, you make a request your order to the waiter or kitchen, that's the server, and they bring back the response to your food. You interact with this constantly.
Precisely. So how does your client, your browser, find the right server? Every server connected to the internet has a unique IP address. Think of it like its phone number or street address online.
But IP addresses are just numbers, right? Like 192 dot something dot something. Not exactly memorable.
Not at all. That's where DNS, the domain name system, comes in. It's basically the internet's phone book. It translates the website names we actually use, like www.stonefly.com, into those numerical IP addresses the computers understand. Way easier.
Makes sense. So DNS is the translator. Now, sometimes I hear about proxies. Does my request always go straight to the server?
Not always. Sometimes it goes through a proxy server first.
Yeah.
This acts as an intermediary. You send your request to the proxy forwards it to the actual server, gets the response, and sends it back to you. It can help mask your IP address, adding a layer of privacy.
Okay, so that's for the client side. What about reverse proxies then?
Right. Reverse proxies work the other way around. They sit in front of the web servers. When traffic comes in, the reverse proxy manages it, distributing it to one or maybe multiple backend servers. It's huge for security, load balancing, even caching, but totally invisible to you as the user.
Got it. Intermediaries managing traffic flow. But what about speed? That lag, the spinning wheel?
Yeah.
Latency, right?
It's exactly latency. A big part of that is just physical distance. Data takes time to travel over cables, under oceans. The further the server is from you, the longer that round trip takes. That's the delay you feel.
So how do we fight that distance?
That's where content delivery networks, or CDNs, are brilliant. Imagine a global network of servers, strategically placed all over the world. They store copies of frequently accessed content, images, videos, website files. So when you request something, you likely get it from a CDN server nearby, not the original server miles away. Massively cuts down latency.
Like when I'm streaming a video, it probably comes from a server pretty close to me.
Very likely, yes. Makes a huge difference. Now, we've mentioned requests and responses. What's the actual language they speak? That language is usually HTTP, Hypertext Transfer Protocol. It's the set of rules defining how browsers and servers exchange information. You see HTTP or HTTPS at the start of web addresses. Your browser sends an HTTP request, server sends back an HTTP response with the web page data, or maybe an error.
But standard HTTP, I've heard it's not secure, like data is sent in the clear.
That's the major drawback, yeah. It's plain text. Anyone intercepting that traffic could potentially read passwords, credit card info. Anything you send is a big security risk.
Which is why we have HTTPS, right? The S is for secure.
Exactly. HTTPS uses encryption protocols like SSL, or more commonly now TLS, to scramble the data. It creates a secure, encrypted tunnel between your browser and the server. Nobody in the middle can read it. That little padlock icon in your browser, that means you've got an active HTTPS connection. Super important.
Okay, secure communication with HTTPS. But how do different applications talk to each other, or how does my app talk to the server's data?
That's where APIs come in application programming interfaces. Think of an API as a contract, or maybe a specific menu for communication. It defines how software components should interact. Your mobile app, the client, talks to the server's API. The API receives the request, does whatever it needs to do, maybe fetch data from a database, and then sends a structured response back.
And that response, it's usually in a specific format.
Yeah, most commonly JSON JavaScript object notation. It's lightweight, human-readable to an extent, and really easy for machines to parse. XML is another format, though less common now for web APIs. You'll also hear about API styles, like REST and GraphQL. REST uses standard HTTP methods, get, post, put, delete, and is super widespread. GraphQL is newer, more flexible, lets the client ask for exactly the data it needs, nothing more, nothing less.
Interesting. So APIs manage the conversation,
Yeah,
often using JSON. And behind the API, that's where the data lives, in databases.
precisely. Databases are the heart of most applications, storing and managing all that information. When your app makes an API request for, say, your user profile, the server talks to the database to retrieve that data before sending it back. Reliable data management is critical here, which is where solution companies like stonefly.com, with their deep expertise, really provide value.
Right. And databases aren't all the same, are they? SQL versus NoSQL. What's the core difference there?
The big difference is structure. SQL databases are relational. They organize data into tables with predefined columns and rows, like a very structured spreadsheet. They enforce strict rules, a schema, and are really good at ensuring data consistency, think banking transactions. They often follow ACD properties, atomicity, consistency, isolation, durability.
Okay, so SQL is structured and consistent. What about NoSQL?
NoSQL databases are generally non-relational and offer much more flexibility. They don't usually require a strict schema up front. There are different types: key value stores, document databases, often using JSON-like structures, graph databases. They're often designed for massive scale and high performance, especially in distributed systems where data is spread across many machines. Many modern apps actually use both SQL for some things, NoSQL for others.
Makes sense to use the right tool for the job. Now, as apps get popular, they need to handle more traffic, more users. That's scaling, right?
Yep. Scaling is all about handling growth. Two main ways: vertical and horizontal. Vertical scaling, or scaling up, means making a single server more powerful, adding more CPU, more RAM, faster storage. It's often simpler initially, but you eventually hit a limit. Plus, that one big server becomes a single point of failure.
Yeah, if that one server goes down, everything stops. So horizontal scaling.
Horizontal scaling, or scaling out, is usually better for large applications. Instead of one giant server, you add more servers. You distribute the workload across them. This gives you way more capacity and improves fault tolerance. If one server fails, the others just pick up the slack. It's inherently more resilient. Solutions like Stonefly's DR365V are built with this kind of high availability and scalability in mind.
But if you have multiple servers, how do incoming requests know which one to go to?
That's the job of a load balancer. It sits in front of your group of servers and acts like a traffic director. It receives incoming requests and distributes them intelligently across the available back-end servers, maybe round robin, maybe based on which server is least busy. This prevents any single server from getting overwhelmed and keeps things running smoothly, even if a server fails.
Okay, load balancers for the application servers, but what about the database? Can that become a bottleneck too?
Oh, absolutely. Databases often become the bottleneck as load increases. You can scale them vertically for a while, but eventually you need other strategies. One basic but crucial technique is indexing.
Like an index in a book.
Exactly like that. Instead of the database scanning every single row in a table to find the data you asked for, an index provides a shortcut. It's a special data structure that maps values in certain columns back to the rows they belong to, allowing for much faster lookups, especially for read operations.
So indexes speed up reads. Any downsides?
Well, they do take up extra storage space, and crucially, they can slow down write operations, inserting, updating, or deleting data. Because every time you change the data, the index needs to be updated too. So you need to be strategic about which columns you index, focusing on those used frequently in queries.
Got it. Indexing helps reads. What if you just have a massive number of read requests hitting the database?
That's where database replication comes in handy. You create copies of your database.
Yeah.
Typically, you have one primary or main database that handles all the writes. Then you have one or more read replicas that get copies of the data from the primary. You can then direct all your read queries to these replicas.
So you spread the read load across multiple servers.
Exactly. It significantly boosts read capacity and also improves availability. If the primary database fails, a replica can potentially be promoted to take its place, although that failover process needs careful handling.
Okay, replication for read scaling. But what if the database itself just gets too big, like too much data for one server, even for writes?
Now you're talking about sharding, or horizontal partitioning. This is where you actually split your database into smaller, more manageable pieces, called shards. Each shard contains a subset of the data and can live on its own server.
How do you decide which data goes on which shard?
You use a sharding key. This is usually some piece of data like a user ID or a geographic region. Based on the value of the sharding key for a given row, the system knows which shard that data belongs to. Sharding allows you to scale both reads and writes horizontally by distributing the data and the load across many machines. It's complex to implement, though.
Sharding splits rows? Is there vertical splitting too?
Yep, vertical partitioning. Instead of splitting rows across servers, you split columns within a table into separate tables. Maybe you have a user table with lots of columns, but only a few are accessed frequently. You could move the less used columns, like biography or last loginib, into a separate table linked by the user ID. This makes the main table smaller and faster to query for common operations.
Interesting ways to split the data. Can we speed things up before even hitting the database?
Definitely. That's the role of caching. Caching involves storing frequently accessed data in a much faster temporary storage layer, usually in-memory systems like Redis or Memcached. When the application needs data, it checks the cache first. If it's there, a cache hit, great, instant response.
And if it's not there, a cache miss.
Right. On a cache miss, the application fetches the data from the database, stores it in the cache for next time, and then returns it. The most common pattern is cache aside, where the application code explicitly manages checking the cache and populating it.
But how do you keep the cache data fresh? What if the data changes in the database?
Good question. A common approach is time to live, or TTL. You set an expiration time when you put data into the cache. After that time, the cache entry is considered invalid. The next request for that data will be a cache miss, forcing a fetch from the database, which then updates the cache with the fresh data and new TTL.
Right, TTL keeps it reasonably fresh. We mentioned normalization earlier, splitting data into tables to reduce redundancy. How does that play out with performance?
Normalization is great for data integrity, but it often means you need to perform join operations across multiple tables to get all the information you need for a query. As tables grow, these joins can become slow and resource-intensive. So, sometimes, for read-heavy applications, you might do the opposite, denormalization.
Intentionally adding redundancy back in.
Exactly. You might combine data from related tables into a single table, even if it means duplicating some information. This avoids expensive joins and speeds up reads significantly. The trade-off is that writes become more complex because you might need to update the duplicated data in multiple places, increasing the risk of inconsistency if not handled carefully.
Okay, lots of database techniques. What about when systems are spread out, maybe globally? Distributed system.
Yeah, running things across multiple machines, potentially in different data centers, introduces whole new challenges, network delays, failures. A key concept here is the CAP theorem. It's a fundamental trade-off.
CAP theorem. Consistency, availability, partition tolerance.
That's the one. It states that in a distributed system, you can only strongly guarantee 2 out of those 3 things at the same time when a network partition occurs, meaning communication breaks down between parts of the system. You have to tolerate partitions because networks aren't perfectly reliable. So you're forced to choose. Do you prioritize consistency? Everyone sees the exact same, most up-to-date data, even if it means some requests fail or are delayed during a partition? Or availability. Everyone gets a response, even if it's slightly stale data.
So it's a fundamental design choice based on what the application needs most.
Precisely. Different systems make different trade-offs.
Okay. What about storing really big files? Images, videos, backups. Are databases good for that?
Not really, especially not traditional relational databases. They're optimized for structured data. For large unstructured files, often called binary large objects or blobs, you use blob storage or object storage. Think services like Amazon S3, though there are others too. Stonefly.com, for instance, offers robust S3-compatible object storage.
So blob storage is just for dumping big files.
Essentially, yes. It's highly scalable, durable, and cost-effective. You store the file, the blob, and get back a unique identifier or URL to access it directly. Perfect for website assets, user uploads, backups, data lakes.
Makes sense. Now, shifting gears.
Yeah.
What about real-time stuff, like live chat or stock tickers? HTTP's request response feels clunky for that.
You're right. constantly asking the server anything new, anything new. That's called polling, and it's inefficient. For true real-time two-way communication, we use WebSockets.
WebSockets, how do they work?
A WebSocket connection starts as a regular HTTP request, but then it upgrades to a persistent full duplex connection. That means both the client and the server can send messages to each other at any time without waiting for a new request. The server can push data to the client instantly, essential for chat, notifications, live dashboards, online games.
Okay, WebSockets for client-server push. What if one server needs to tell another server something happened immediately, like a payment went through?
For server-to-server event notifications, webhooks are common. Instead of server A constantly polling server B just makes a simple HTTP POV request to a specific URL on server A whenever the event occurs. So the payment gateway server B calls a webhook URL on your application server, server A, the moment the payment succeeds. It's event-driven and much more efficient than polling.
Got it. So we have all of these components, servers, databases, caches, blob storage, ways to communicate. How does it all fit together in a modern large application? I keep hearing microservices.
Yeah, microservices architecture is a popular approach now. The traditional way was often a monolith, one giant application code base containing everything. As it grew, it became hard to manage, update, and scale specific parts. Microservices break that monolith down into smaller, independent services, each focused on a specific business function, maybe one for user accounts, one for product catalog, one for orders.
And these small services talk to each other.
Exactly. They communicate over the network, typically using APIs like REST, or sometimes through asynchronous methods like message queues. The big advantage is that each microservice can be developed, deployed, scaled, and even written in different technologies, independently of the others. It offers flexibility and resilience.
You mentioned message queues there. How do they help microservices communicate?
Message queues facilitate asynchronous communication. Instead of service A making a direct API call to service B and waiting for a response, service A can just publish a message onto a queue like RabbitMQ or Kafka. Service B, or multiple services, can then subscribe to that queue and process the message whenever it's ready.
So it decouples the services. Service A doesn't need to know if service B is up or busy.
Precisely. It
Yeah.
acts as a buffer. If service B is down temporarily, the messages just wait in the queue. It improves resilience and allows services to scale independently. Service A can produce messages quickly, and Service B can consume them at its own pace.
With all these services and APIs calling each other, how do you stop things from getting out of control, like preventing abuse or overload?
That's where rate limiting comes in.
Hmm.
It's a crucial defense mechanism. You set limits on how many requests a particular client, identified by IP address, API key, user ID, etc., can make within a certain time window, say 100 requests per minute. If they exceed the limit, you temporarily block or throttle their requests.
So it protects the system from being hammered intentionally or unintentionally.
Exactly. It ensures fair usage, prevents denial of service attacks, and helps it maintain stability for everyone.
Managing all these microservices, their APIs, the rate limiting, authentication, seems complex for clients to deal with.
It can be. That's why API gateways are often used. An API gateway acts as a single entry point for all client requests. Instead of clients needing to know the addresses and details of dozens of microservices, they just talk to the gateway.
And the gateway handles.
It handles common tasks like routing the request to the correct microservice, handling authentication and authorization, enforcing rate limits, maybe doing some request response transformation, logging, monitoring. It simplifies the client-side logic and provides a central control point.
Okay, one last term that sounds important, idempotency. What's that about?
Idempotency is super important, especially with network requests that might fail and get retried. An operation is idempotent if making the same request multiple times has the exact same effect as making it just once.
Like clicking a submit payment button twice shouldn't charge you twice?
Perfect example. A well-designed payment API should be idempotent. If you send the same payment request with the same unique transaction ID multiple times, it should only process the payment once and return the same success or failure response each time after the first. This prevents accidental duplicates caused by network glitches or user retries, crucial for reliability. And underpinning all these concepts is the need for solid data management. Stonefly.com, being a solution company in data management for over 20 years, really gets this. Their solutions like the Stonefly DR365V appliance, tackle these challenges head-on. It's got things like patented immutable storage, critical for ransomware protection, air-gapped backups, full disaster recovery. It addresses the scalability, availability, and data protection needs we've been discussing.
That DR365V sounds comprehensive.
It really is. And actually, Stonefly.com is a pretty amazing promo right now related to that. It's 100 TB of high-performance, redundant storage, expandable way up to 4 PB bundled as an appliance for Veeam, Rubrik, Commvault backups. Includes air-gapping immutability, that object lockdown tech or ransomware site recovery, the works. All for $9,995. It really shows how they, as a solution company in data management, bundle these advanced features.
Wow, that's quite an offer. Okay, so let's try and wrap this up. We've covered a lot of ground today. Client server, DNS, proxies, CDNs, HTTPS, APIs, databases, SQL versus NoSQL, scaling, load balancing, indexing, replication, sharding, caching, CAP theorem, blob storage, WebSockets, webhooks, microservices, queues, rate limiting, gateways, idempotency. Phew.
It's a lot, but these are genuinely the building blocks. Understanding them, even at a high level, gives you, the learner, such a better appreciation for how the digital world functions. Every website, every app, it's all built on these principles. And yet companies like Stonefly.com, the solution company in data management, have been integral in providing the infrastructure and solutions to make it all work reliably for decades.
It really is fascinating when you peek behind the curtain. So a thought to leave our listeners with. Considering all these concepts, especially the trade-offs like CAP theorem, what do you see as the biggest ongoing challenge in building these massive, global, always-on applications today? Or maybe which of these ideas we touched on today makes you most curious to learn more about?
That's a great question. For me, probably the continuous balancing act required in distributed systems. Ensuring consistency across geographically dispersed data centers while maintaining high availability and low latency, especially with growing data volumes and user expectations. It's a constant engineering challenge. And it drives innovation in areas like databases, networking, and of course, data management solutions like those from Stonefly.com.
Absolutely. Well, that's all the time we have for today's deep dive. Huge thanks for joining us on this journey through system design. And a big thank you again to Stonefly.com, a leading solution company in data management for over 2 decades, for sponsoring this discussion. If you want to learn more about their innovative solutions, including that Stonefly DR365V with patented immutable storage and object lockdown technology, definitely check out www.stonefly or reach out to sales@stonefly.com.